Utpal did his PhD from Physical Research Laboratory. His expertise is in nonlinear systems, both involving optics and also cold atoms. So now, for example, he has gotten into this quantum computation and basic aspects of cold atoms and these quantum domains very quickly, particularly generation of different kind of quantum states, the soft Planck structures and their utilization for quantum metrology. For example, recently I read his beautiful paper on this negative temperature. So many of these things, for example, where light and matter are coming in a big way, interaction of that is where both expertise lies. So now the field is yours. You have up to 1, right? So you take some amount, give some amount for questioning also. Huh?
Yeah, so I think it is up to 130, sir.
Up to 130. Yeah. You can take up to 130.
Yeah, so
like
probably 115 or so. I'll continue. Then I'll take a question. Yeah. So that's what. Yeah. Okay, sir. Thank you. And so I am very happy to. Let me first, share my screen so that at least the title is visible. I hope my screen is visible. Yeah, okay. So first of all, I'm very happy to present my work in QIQT 2021 and thank the organizer, especially Professor Panikrai. And it was already a very successful event last time. And this time I can see that this is going very successfully, even if it is online. And it cannot be better than getting introduced from the own supervisor, because he knows the inside and outside of my academic endeavors. So thank you so much, sir. I will start the talk now. So this is the coming back to the title. So this is I'll be talking about Bose-Einstein condensate, quantum simulation, and quantum information. So I think this is the first talk in this direction. So and this is a summer school. So I'll spend some time in the beginning for introducing the system and the motivation for such kind of applications. So I'll slowly, try to get into the applications which are actually going on and our group is working on, but then I'll start from the 0th level. So this will be a more or less, outline. As I said, that I'll start from the introduction of the system, and then why, quantum simulation is required and why it is an appropriate, system for quantum simulation. There's some of the application for quantum information and applications as well. So I would like to start from this statement. There are many complex systems, especially quantum system, and where observing the phenomena, novel phenomena, is not very easy, and the main reason behind it is since years and decades, and Feynman has kind of stated that maybe we can use another simpler, controllable quantum system to simulate, understand, and control this phenomena. So I would like to emphasize 2 points here. The system has to be controllable, like the system which I'm using for such kind of formulating the phenomena for other system, that is supposed to be controllable, and it has to have a lot of applications. So this is the kind of motivation behind the field, probably quantum simulation. So you utilize a quantum system which is very controllable and useful as well, and to mimic other quantum system in that. Okay. And here, I tried to draw some analogy, which I have taken, this picture I've taken from internet. This has come from science paper long back, but this is a STM image of the array of, circular arrays of atoms, large number of atoms. You can see the peak, and all these peaks are all copper atoms. And In the middle, you can see that there are interferences happening. Now, the thing is that, why the interference is of that shape particularly? Probably it is not very easy to understand in condensed matter system. So maybe we can have a kind of a similar model like in 2015. Some of us, we have given this idea that array of coherent states in a circle can create a similar situation. And we did not mention about esteem image, but I think there's a good shown that the origin of this such kind of interference region, this is only in the center, towards the center, but if we extend, then you can see the coherent states. So periphery is actually visible here, and the interference, central interference is here. So you can have a very beautiful analogy of by modeling a quantum system, which is known to the people, physicists already, and then kind of to understand the phenomena for another system. So that's a kind of a attempt since years. So this is some connection which I wanted to show to the students. And yeah, so how to go ahead with matter waves or ultra cold atoms? That's our main goal is. And if you look at this, is combination of two things which is contradictory. So it is also having a word matter and also waves. So that's the thing, it makes it very confusing to start with, and at the same time it becomes very interesting. So I'll try to kind of unravel this meaning of this. So why it is so. So the natural question is whether it is a matter or a wave. Now, I would like to mention that this is a very well-known, self-identity problem of photon. So when photon is thinking about its own frequency, whether it is an X-ray regime or a visible regime, and then it goes back and asks the same questions. Yeah. So I do not understand whether I'm a wave or particle. So forget about thinking about my frequency. So it's a self-identity problem of photon, and so it's a cartoon of that. And the same thing, happens to matter. So what de Broglie says is a very beautiful thing, that nature loves symmetry. So if radiation, which is basically a wave, can exhibit particle nature under certain circumstances, and since nature likes symmetry, then entities which exhibit particle nature ordinarily should also exhibit wave nature under suitable circumstances. So we have to notice few things here, that suitable circumstances, that is important. And the particle which actually and he has given this formula that is very well known to the students, that h by p, which is related to the momentum, and momentum is related to velocity and the mass. So it is a kind of a very kind of a easy homework for the students to check that what is the range of de Broglie wavelength. If you take an example of electron and try to find out, take some speed, which is, in general, and then you can see that it is in the order of 10 to the minus 10 meter. Whereas, the free electrons has a different studies saying that different kind of dimension of electron. But, if you consider the 10 to the minus 18 meter, then you can already understand that de Broglie wave is much larger than the dimension of the electron. Okay, so it is dominating. So you can consider an electron as wave. Whereas if you just consider a ball, which is a macroscopic, say, football, and you can see the de Broglie wavelength is 10 to the minus 34, whereas the dimension is 1/10 of a meter. So it's a 10 to the power minus into 10 to the minus 5 times lesser than the dimension of the ball. So already it is very, very negligible. You cannot consider the de Broglie wave, and it is not appreciable. It is negligible for a ball. So that's a quite obvious thing for students to check by their own. Okay, so now let me mention very important discovery in this line, because with the beginning of quantum mechanics, when it started the idea of quantization started from black body radiation. So when Planck has, kind of mentioned that, radiation can be composed of, it is quantized. And then it also gives the formula of energy density in a particular frequency range. Now, the many, eminent scientists and mathematicians, they have tried to derive this formula, Planck's formula. You can see in the letter, this was the letter from Satyendranath Bose to Einstein in 1924, because the font is smaller, so I'm telling you. So it is about the derivation of the Planck's formula. Now, Einstein also tried to derive this by, his own Einstein's A, B coefficients, but then he could not finally succeed, because he had to finally force match this formula. It was not a foolproof derivation, but he force matched the formula by taking some coefficients A and B, which is from the formula given by Planck himself. So later, Satyendranath Bose came, and he has taken very bold steps by saying that particles are indistinguishable. Say here, the photons are indistinguishable, because the Einstein, when he tried to derive in 1916 probably, and he was not having an idea of indistinguishability of the particles. Okay, and then Bose has started that, and then he also said they are of integral spin, and there is no limitation that a particle can be in a particular energy. So these are the very important statements he has given and used in his derivations to find the exact derivation of the blackbody radiation formula. So that was the starting point and the discovery of quantum statistics. It's a very big field. The particles, a statistical system can be thought of as quantum system. Now is the easiest approach from the textbook, that if you consider just two particles, 1 and 2, with two systems A and B, then the wave function can be written like this. But if you swap the particle, and the wave function also kind of written in an obvious way, this manner, but Hamiltonian is unchanged. And these things tells you and suggests you to take some superposition general eigenstates, and finally you actually get two combinations of the eigenstate if you apply the normalization. Then this is the symmetric wave function psi s, and this is the antisymmetric wave function. The point which I want to mention is that if you take these two particles identical, so the idea of the Bose is indistinguishable particles. If they're indistinguishable, then 1 and 2, they are identical. So the antisymmetric wave function vanishes, whereas the symmetric wave function still exists. So that means that there may be many number of bosons, or the particles with symmetric wave function in a single quantum state, okay, single state. And that's actually the violation of Pauli's exclusion principle for bosons. Later it was named as bosons and fermions, but fermions obey Pauli's exclusion principle. So what is the take home from here? That bosons can, a large number of bosons can occupy a single quantum state. So that's the idea, we get it from here. And we actually go to the distribution now. And this is in connection to the letter which I have shown in the beginning, from Bose to Einstein in 1924. And then Einstein modified this for massive particles. So it was for photon, but Einstein said, okay, it is also applicable for atoms. And you can actually introduce the chemical potential in it, and then it is a Bose-Einstein distribution formula. Okay. Now, if you look at the high temperature limit, what happens that there are a large number of levels among which the particles are distributed. Okay, and effectively the chemical potential becomes very, very less compared to the minimum allowed energy of the system. So in this fashion, if you just take the distribution, this term is dominating over 1, and then it goes to the classical MB distribution, Maxwell-Boltzmann distribution. So this is a very well-known fact. Now, the interesting part here is low temperature limit. So if you go to a very low temperature, then what happens, that chemical potential slowly rises, and then at absolute zero temperature, this chemical potential will be equal to the minimum energy available to the system, okay, to the lowest temperature. And then if you take this limit here, then you can see the denominator goes to 0, and this distribution function blows up And this is proportional to the number of atoms, right? So F, E, G, and D. So in a given energy range, so if you take a particular energy, so number of particles will be infinite. Once you take the energy minimum is chemical potential, which happens at a very low temperature. So the number of particles in single particle ground state becomes arbitrarily large from the B distributions. Okay. So here I state that this is the statement taken from Pitowski. At low temperature, significant proportion of atoms in a gas condensate in a state of lowest energy of the system, and that is nothing but Bose-Einstein condensation. Now, to understand more about it, you can see the left is a distribution function itself. Just look at this temperature. If you reduce the temperature, go to towards the negative side of the axis, temperature axis is scaled by the critical temperature. Then it suddenly beyond critical, the atoms in the ground state suddenly rises, and you reach to 1. That means all the atoms are in the ground state at absolute zero temperature. Okay. So what is actually happening that in normal temperature you have the atoms distributed among various energy levels, and but if you cool down the gas to a very ultra low temperature, then they go to the ground state. Okay. But the thing is, what is happening actually, if you look at the de Broglie wave, which I have started with, that in normal temperature you see that they are like billiard balls, and this is the picture taken from the presentation by Ketterly, and then if you lower the temperature, you see that there are small de Broglie wave which is going to appear because it is proportional to the square root of the temperature. If you lower the temperature, de Broglie wavelength will be higher gradually. And then at critical temperature, this is a very important junction here, that you can see a bold red state, which is a giant matter. And this is produced due to the superposition of matter waves of the atoms. So actually the atom, they start talking each other. Their waves are, kind of slowly becoming coherent. And these red lines are actually the coherent superposition states of those waves. So it is no more a classical system. It is a purely quantum, because this is a quantum superposition. But yes, in addition to that, there are some thermal fluctuations because you are still in a finite temperature, not at absolute zero temperature. So if you go to the absolute zero temperature, there is no thermal cloud because your temperature is zero, but this is still kind of a virtual point yet to be reached, because people are able to reach only up to few nanokelvin. So this is the idea behind why this system is important, that at low temperature, below critical temperature, it goes to a completely quantum system, and you see that large number of atoms, they create a single quantum state. Okay, they are not kind of distinguishable beyond critical temperature, rather they are creating a wave packet. So this is the wave packet which I'm talking about of matter, and this is the pictures from the experiment of rubidium-87 in Boulder. Taking the picture over there. But if you see, there is no BEC in the beginning, but when it starts to cross the critical temperature, there is a sudden rise in the density, and it goes on, and this yellow region, which is a thermal cloud, it gradually becomes negligible. Now, this is the simulation, done by them, that there are two thermometers here. And the left one is the critical temperature, and right one is the temperature of the system. Now, if you lower the temperature, when it crosses the critical one, the other one, then suddenly there is a jump in the atomic density. Okay, and that's the point where you get BEC, and the system goes to the quantum regime. Okay, and remember that this is in the momentum space, so you can see the axis over there is a Vx and Vz. So it's the momentum in X and Z direction. So all these things are visualized in momentum space. Okay. Now, as we're talking about this, experimental movie, so, it took 70 years after this theoretical discovery by Bose and Einstein, and Cornell and Neumann from Boulder and Ketterle from MIT, they have simultaneously done the experiments of rubidium-87 and sodium almost at the same time, and got the Nobel Prize in 2001. So it took 70 years because it was a tough experiment to take the system, to take any system to such low temperature where they remain in a situation that the interactions are not too much and they still remain in a position to lower the temperature. So if the interactions is too high, then it actually prohibits the further cooling of the sample. So that's the hurdles they have faced, and found that alkali metal gas may be a most favorable candidate. But now there are many species for which the BEC is obtained. Now there are some salient points. BEC occurred in momentum space, which I already mentioned, not in coordinate space. Condensate is a highly tunable object. It also has long coherence time. That means it remains coherent for very longer time. And condensate is purely of quantum origin. Now, as we are talking about this, the experiment, so it is worth to, kind of mention the salient steps where, laser cooling using Doppler shift. This is a very beautiful method that, when the atoms are moving inside an alkali gas, and then a laser is also applied to that, and then it can also cool it because of the Doppler shift. So the atoms which sees the frequency, higher frequency of the laser, it absorbs, and when it emits the energy which is higher than it has absorbed. So that's how the system is being cooled. But the difficulty here is you have to continuously tune the laser along with the changing of the velocity of the atom. But so there is a limit of this, and then the further things happen due to evaporating cooling. But then after magneto-optical trap, so you have to trap the atoms using lasers and magnetic trap. So these are the main steps. This is the MIT lab when I visited there. So this was the atom laser lab, and these are two BEC lab what I have seen that time. So so that's the kind of setup they have. Okay, so now is the main thing that we have to have theoretical approach that how we can probe into the application of quantum simulation with matter waves, whether matter waves is really useful in that. So already some of the hints I have mentioned here that the matter wave. So initially we asked the questions whether it is matter or wave. It is a wave of matter. So the answer is a wave of matter, and it is a very much coherent. Okay, so it remains coherent for longer distance. That's a very positive thing for that. And the next thing is it's very, very controllable. So it's a repeat slide, but I would like to mention about the sequence that first of all, it is a quantum, a purely quantum state, and is a highly tunable. So how do I connect it? So it's a quantum state, highly tunable, and then it occurs in momentum space. So that means that tunability should be used to also kind of confine this system in coordinate space. So it is an obvious kind of attempt should be after the discovery, experimental discovery, that it has to be controlled by the tunability of the system in coordinate space. So that's the thing. So the tunability, I mean that from outside, you can use some kind of potential, quantum mechanical potential to control the system. Now here, some examples which, I don't know why this panel is visible at all. Anyway, I don't think it is appearing on the other side. Okay. So these are some examples. It's randomly I have collected, but there are thousands of such things that discovery of solitons, and then phase transitions, Anderson localization, negative temperature, and BEC in space station, and so on. So all these things gives you the motivation that the how much the system is controllable. In 2020-21, there are beautiful papers of interferometry, Signac interferometer, and so on, and many others, super solidity and many more. So all these things, relying on the fact that external trap, the trap which you are using from outside, the potential you are using from outside, is actually is the prime factor for controlling the BSE. Okay, so that's the thing, I wanted to point out. So first of all, it is very much useful because you can see a lot of technological advancement over there, and because it is highly tunable and it is feasible to outside fields, so it is natural to think of engineering the external trap to find out new phenomena and applications. So the one of them is quantum simulations. When you have a situation of like lattice, like superfluid mountain insulated transitions, and there are many more, and then you can have a situation of quantum simulation. I don't know whether this heading is visible. Can someone tell me whether this heading is visible? I don't know, because it is obstructing this, Zoom.
Dynamics of Bose-Einstein condensate.
Yeah, but is it visible when I make a slideshow?
Yes, it's visible.
Oh, okay. So it may be only in my screen that, Zoom tag is obstructing that. It's fine. So, yeah. So we should not forget that, when you have, you try to build up a theoretical equation, dynamical equation for this, this is a second quantized Hamiltonian which you start with, and where, H naught is single particle Hamiltonian, and U is external trap, which this is the interaction term, which between the atoms, okay, between the particles. Now, what about this interaction is, because it is a low energy, you are actually working with situation where you can model the system by kind of contact interaction, and then finally achieve to a dynamical equation, which almost look like a Schrodinger equation. But there is a difference of this, blue circle, which is the nonlinearity, which is arising from the interaction itself. So because the atoms are interacting each other, it is no more a simple Schrodinger equation. It gives you a nonlinear term in it, and which makes the system different in many ways. First of all, it is mathematical structure is completely different. Its physical formation mechanism of the solutions are different, and applications too. But more than that, it becomes very non-trivial when you deal with analytical methods. So, it is worth starting from this paper. If a student wants to kind of explore the mathematical things, how you can have a self-similar solution in this system, because self-similar solution like soliton is a basic solution, is a very useful solution in any nonlinear system. You can have it in mechanical system and pure optical system. And this is a soliton in quantum system. So because it is a self-similar and it remains, kind of stable for longer time. So a lot of experiments have been gone through in these directions. But, in lower dimensions, the solitons are more stable than higher dimension in 3 dimension. In 3 dimension, there are some limitations. So this is the approach given by Rajni Shatre, Professor Panigre, and Professor Agrawal in 2006, where you can see that in presence of harmonic confinement, one can actually find out exact solitonic solution, which can move with time and can have very interesting properties. So that's a beautiful starting point to derive this paper. And then as a natural question that, can you, because you have to engineer the trap, so is it possible that you can have some general approach? Because the general approach in the sense, in terms of the potential, I mean. So what should be the key point here? So what we have actually taken up, that we have made the answers very, very general. And why it is general? Because we actually eliminate the possibility that restriction in the answer should not eliminate any solution from the system. So you take it a very general answer, you try for that. So when we started with from nothing. So we did not know whether we are going to reach to a final point. But then the idea was, let us take a bit. So, and then finally we have some set of equations which we say consistency equations, because this condition has to be simultaneously satisfied. Okay, and you can see these parameters. You know, everything, theta, phase, all are space and time dependent. So we are keeping it very general to start with, and then one by one this can be solved in a general form, and then according to the applications you can finally use as per the experiment. Okay, so that's the approach we have given, but this actually not for a single potential, this is for a multiple potential. You can actually finally you can have a number of situations. Like this is the potential, which looks very complicated, but if you take a particular example of some physical scenario based on some experiment or some discovered phenomena, then you'll be getting the result. You may get the result accordingly. So this was the method we actually started in 2014. And this is the recent one, which we published in 2020. I'm just telling you in a slide because this is a beautiful example for studying the BEC in presence of the trap. Is the first method had the potential is time dependent, exact method, potential is time dependent, and you are actually able to deal with a power law up to 6th power. Along with that, you can also have exponential terms in it. So there are a lot of possibilities. Double L is a basic kind of outcome of this result, but there are many more you can have, power law potentials and many more from this potential. So yeah. Now the question of quantum simulations. Now that we are convinced that this system is very useful and tunable too, and the external trap is a factor where we have to actually look at it very carefully, then how we can go for quantum simulation. Now, quantum simulation for disordered lattice. If we have a lattice and there are disorderness, that's a very typical situation in condensed matter physics. And there are many phenomena which you actually intuitively understand, but not able to kind of have the proper explanation of it. So what is being done is this lattice is for BEC, it is replaced by optical lattice. So if you can see the red word, which is optical lattice, and if you replace the lattice by create an environment where the optical lattice will kind of a similar situation of the condensed matter lattice, and then you observe the atoms over there, and that will create a situation of quantum simulation. So why bichromatic? Because if you superpose two optical lattices of two different frequencies, that creates the disorderness in the potential, optical potential. Now, optical lattice, just for the students, I can say in simple statements that if you have two laser, equivalent lasers, same laser, counter propagating and superposed to each other, and then you can have a standing wave generated. Okay, and the standing wave, the waves are moving, but standing waves maxima minima, they are not moving. So actually this minima can actually trap neutral atoms. So that's the idea of optical lattice. And then if you have two optical lattices with different angles between them and different phase relations between them, you can actually have a variety of optical lattices in lab very easily. So this has become one of the best system and situation for quantum simulation in this area. Okay. Now here is kind of a pictorial thing, and there are large number of papers in that, but this is the one where it is beautifully explained in PRL 2012 that this is a short wave optical lattice. This is the standing wave which is having the lesser wavelength. This is the optical lattice which is the larger wavelength, and then if you superpose this green and the pink one, and then you get the black one which is having a kind of the small minima, not this one. So this is the main site of the optical lattice, and this is the frustrated site. Okay, the frustrated side, and or the disordered positions I can see in the optical lattice. That's how you can create it. And so there have been a lot of experiments. So this field is much ahead of, the experiment is much ahead compared to theory, because it's not so easy to prove in theoretical front. So this is a beautiful, experiment in 2008, where you can see that there's a strong localization in quasi 1D PEC for such kind of disordered potential. So they call it Anderson localization. Okay, so this was the experiment, and they have clearly found that beyond certain disorderness, the atomic density goes suddenly very high, and just like it happens in Anderson localization. Now we tried to kind of model this system by this potential bichromatic lattice. You can see in the middle that V1 cos twice Lz and V2 cos Lz. So there are two frequencies, which is one is double of other, and two different intensities, and then you can have a similar situation, like just like it was mentioned in the paper PRL 2012. Okay, so I'm not putting the methods here, but just the final results here. That the solutions are definitely related to elliptic functions, but if you look at the here, for simplicity we have taken time independent solution, but in principle one can have time dependence in the method. But even in time independent method, if you see the variables, and that actually kind of imprints the information of the potential. Okay, and so the potential expressions that can actually have the effect on the elliptic functions over there, and you can get the wave functions accordingly. So this we have reported in 2014 again in laser physics letters for the attractive and repulsive both cases. So here the main point is that tunability, like we have been talking about the simulation. So getting a one instant is good, but you have to have the tunability in experiment. So how you can tune it is if you look at the this amplitude part, the intensity part of the optical lattices, they are related to L square because they are related to recoil energies and all. So, but how the other factors, how the disordered term is appearing over there, and these two beta and L will actually control the potential. So the idea is not taking the potential and getting the solitary wave. So I do not know the potential. I only know a particular form, which I expect that the potential to be in this form, but I do not know what is the relation between V1 and V2. So I have to have a particular relation which is physically relevant. At the same time, it can have a stable solitary wave in that. So these are related, and that is also reflected in the solution. So this is, I just picturized this, solution over here is very interesting that if you have the optical lattice in the beginning, so if beta equals to 0, so we have also, kind of investigated like, the situation where frustration parameter beta 0 and frustration parameter beta is very high. Okay, and then you can have a shape parameter of the potential, which gives you the ratio between the frustrated depth and main depth. So if it is very small, then it is nothing but an optical lattice. So it gives you a simple bright soliton. It does not see the ups and downs in the potential, because potential is very, very, depth is very, very less. Okay, they are not upscaled. This scale which you see, the potential density is not, density scaling is not given. So beta value, you see that the depth of the potential is increasing, and at the same time the atoms are able to see the potential depths. So they are getting maxima at the minima positions, and then when this frustrated things comes up, so there's a big jump 0.5 to 4, but you can have a smooth transitions and see that how it goes on. But when you actually go to a 4, this frustrated position is going to go to a negative side, so a negative energy. As soon as it goes to the negative energy, because of the attraction of the atoms, it goes to the main side, to the frustrated side. So they jumps over there in the middle. So it's just a starting point. Now, immediately after that, all the atoms comes to the center. And that's a clear signature of Anderson localization, which was reported in the experiment. Okay. Now we have actually verified in various ways. These are the two of them, the atom fraction. So the fraction of atoms, you can see this is the N naught, the number of atoms in the central site, and that goes up and it goes to 1 because it is the ratio with respect to the total one. 1 means that all atoms goes to the central site. And with respect to the energy, as the depth of the lattice goes down, it goes down, but then when it jumps to the frustrated site, and then it goes up, and finally, when it is same with the previous one, initially you started with the ground state and then it goes back there, and then it again goes to the 0. So it's the energy and number fraction to support the result. Now is another important aspect that what is actually done in repulsive interaction. So repulsive interaction means the atoms are pulling each other away from each other, okay? And what is happening that, when the optical lattice is a lesser depth, then you see a simple dark soliton because it is touching at 0 and with a background. So it's a simple dark soliton. But when you have a larger depth of the optical lattice, the background is actually getting affected by the lattice, and it goes on like this. But beyond 4.5, you can see very interesting situation that that background atoms are actually modulated by these oscillations, and it is actually effectively an array of bright solitary trains. So this may be a new way in repulsive interaction, but the background atoms are used for getting bright trains of solitons. So yeah, so this is reported already. Now, so as we have given the kind of idea that how this bichromatic lattice can simulate Bose-Einstein, using Bose-Einstein condensate can simulate situations of disordered lattices. Now, what is the situation of negative absolute temperature? This negative absolute temperature is not a new concept. It is a very well-known concept in statistical physics. So the idea is that when you have, so in normal temperature, you have lesser number of atoms in the higher energy levels, okay? And so when energy is increasing, you have lesser number of atoms. But in the lower energy levels, you see more number of atoms. So that is in M distribution, B distributions, everywhere you see the similar thing. But if you create a situation that the energy is upper bound, that means that you have a stable state created at the higher energy state. So more number of atoms, the probability of the quantum state or the atoms is more in higher energy compared to the lower energy. So the question is how to explain this in terms of the distribution function, B distribution functions. If the B distribution functions to go right, then the only way you can explain that is putting T2 minus T. So you have to go to a completely different, temperature scale, not to 0 to very high temperature, but to -0 to -infinity. So this is the scale which I'm talking about, a negative absolute temperature. So when you have energy upper bound and have density, higher density in higher energy level compared to the lower one, you have a situation of negative temperature. Now, this is the experiment in Science 2013 that this is the situation of positive temperature, which I mentioned. The probability goes down if you have the larger energy, right? And so, and in negative temperature scenario, the energy is increased, you see the atoms are, number of atoms probability is going up, okay? And that's the situation completely contrary to the situation of positive temperature. Now, what is the big deal? That, so far, before 2013, this negative absolute temperature was not realized in any physical system. So this is the first time it was realized for ultra-cold atoms, BAC. And that is why it has started a new domain of applications and in negative temperature domain, okay? So this is by the explanation by L.D. Carr and the same plot here. And you can see the potential. The potential is harmonic and the optical lattice. So what they do is experimentally, they trap atoms and then they make it expulsive to make a bound states in the higher energy. to trap more atoms over there. Okay, so it's a very beautiful experiment and to achieve negative temperature. So now you have to understand one thing, that in the beginning, okay, this is again the process which is reflecting here. You can see the atoms, the dots are atoms. These are some schematic of their experiment they have given. But if you look at the momentum space, what is happening that in positive temperature, you have the localization in the center of the momentum space. And at negative absolute temperature, you have the localization in larger momentum. So higher energy states are more occupied. Okay, so this is the kind of potential they have given. Okay, and they have beautifully have controlled these parameters, this MT and NT, to achieve such kind of thing. So you have a expulsive harmonic trap, and then you have oscillations. Is a oscillatory modulation over there. Now the thing is, our idea was that can we have a better situation? So better in what sense? That optical lattice, as from the previous explanation, previous study, we have seen that bichromatic lattice is more favorable to trap atoms at the center. Okay, so it gives you a more stable state compared to an optical lattice. Okay, in a given amount of frustration of the lattice. So what we do is we modify this thing. So of course, you know, a limiting case of this bichromatic lattice goes to this optical lattice, of course, which I have mentioned in my last few slides, that one of the special cases of this lattice is optical lattice. So you are actually including this optical lattice. In addition, you also are creating, like, you know, a situation which can actually trap atoms in a better way. So you expect a more stable negative temperature system, and in addition, maybe the temperature is more negative. So it's more stable, more negative. So let us see what is happening over there. We have taken a very, very general potential. You can see all the experiment, all the parameters are time dependent, and of course there is a bichromatic term 2L and L sitting over there. So these are the these are the final results, and now let us see the density. You see, it is beautifully located for higher frustration. Is beautifully located at the point of the frustration. So although it is an expulsive trap, it is not a confining trap, just like harmonic trap, which can trap atoms like any. We know that particle inside harmonic world, they oscillate inside the trap and they remain there because that's a bound state. So this is the bound state at higher energy. So energy is upper bound. You cannot go beyond that. So the upper bound is a completely different situation than the situation we all normally consider in while solving Schrodinger equation for solvable systems. Okay, so that's the situation we create. But you know, quantitatively we have measured the things, and here you can see is a time dependent thing. So in addition to applications in atom interferometry, and people are actually creating a situation of atom distillation. So when the atom is actually transported from one side to another in a controlled manner, so that is possible if you tilt the potential. So that is also done in negative temperature domain. So you can see this figure is the density, and it is going from one to another, and that is done by kind of a linear trap, a simple linear trap with time dependent factors. So linear trap is very easily kind of achievable in experiment. There are a number of experiments in that. So one can actually add, in addition to BOL, linear trap with time dependent chapping, so that it can go to one way to another, seeing the atom transport at negative temperature. Now there are quantitative analysis. There are more. I have just given some examples of that. You can see the value of the energy temperature from the definition of the temperature here. And for higher, you know, frustration, you get more negative temperature. Okay, is the temperature is going much more negative if you actually increase the frustration. That was the intention of taking a BOL trap. So we considered that the system model which was considered earlier, this is much better one. Okay, and of course we analyze this as a stability, and the profile of the trap has a lot of important things to do with the amount of temperature. So we have analyzed those things later on, but this is the one which is directly related to the obtaining of the temperature. So fine. So now some more things. So far, I have addressed for bichromatic lattice and a new domain of quantum simulation, which is in negative absolute temperature. Now, I would like to mention just very briefly that what happens to a very new kind of wave, which is rho wave, and because the large number of student participants, and that is why I included this. These are some ongoing things we have communicated already, that this rho wave is the some which appears from nowhere and disappears somewhere. Okay, so is completely mysterious, and the formation mechanism is not known, and so it's very difficult to understand what is actually going on. But if you try to, but it definitely will happen for the nonlinear system. Just like in a soliton, it is also having a very steeper height, and at the same time, it also have a dip along with the density peak. So that's a very different kind of properties of this wave, which is actually seen in reality. Now, people have been observing in BC, like people have been studying in BC in different context. But here we have taken this towards quantum simulation by introducing an optical lattice and a bichromatic and disorderness of that. So single component and two component both can be addressed with solitary waves and solitons. Solitary is a rho wave, and rhogons actually. So I'll just show you something that which is of first order, second order solutions of rho wave, and interestingly, things are not visible here. If you see the rho wave over here, and if you increase the frustration, you see in the position, it also it almost becomes like a kind of oscillatory. It goes to a scenario of optical lattice, but then there is something in between which is not visible. So I will show you that what is there in between. So at the center, there is still a rho wave persisting there. So it is the rho wave is actually localized over there. So it is equivalent to a kind of a Anderson localization of the rho wave at the center for higher frustrations. So if you see a negative region over there, that is still persisting till very high frustration of the lattice. Okay. Now, this is one instance for engineered optical lattice. So when you deal with optical lattice, you should bring to the situation that, well, in experiment, always it is not that, you are combining L and 2L. So you can also have a combinations of other things. Then there can be different frequencies, because the shape, if you just want to tune the potential, it may not be possible with two frequencies only. So you may be needing more frequencies than two. So such situation, we have addressed here. So we are able to have 2, 3, 4, and up to 6 frequencies combination, different kind of combinations, and all with experimental parameters. Okay, and some just 2D plots I'm showing. I'm not because included the mathematics, because then it will be monotonous. So yeah, so some examples where the potentials are more or less people have seen of such kind of potential, except this disorderness. So it is a double L superlattice with disorder. Okay, and then you can tune the disorder, you can tune the depth of the lattice, you can tune the position of the lattice, and so on. And then you can also have a different kind of potential, other kind of shape that you can see from. So this is all potential, not the density. So it's changing the parameter can take you from one end to another. Okay, so this is about the engineering lattice and the quantum simulation. These are some snapshots of the density which we for the engineering simulation environment, for which the ultra-cold atom is already very useful. And so can it be used because it's a highly coherent object, highly controllable, So can this be used for quantum information? So that is obvious reason. So, and there have been a lot of studies. It's not that, there's no study. There have been a lot of directions people have been working on, because this system is a very beautiful candidate for such things, quantum technology. Now, I'll especially mention about our recent work on matter wave fractional revivals in ring waveguide. So what we do is we actually take a very well-known system. So a BEC in a ring waveguide is a very, very well-studied system, very, very well-studied. There have been a number of experiments and different ways people have observed persistent flow of clouds, and everything, lifetime, everything is more or less known in this system. So that's why we have taken up, and so that people can actually think of new things. So here, what we do is a ring trap. I'll tell you how to create this trap, but for the time being, what actually we are going to do here in the ring trap, the red circle is the BEC. And now we observe this system for a very longer time. And what you see is the condensate atom being very coherent, they bifurcates in different numbers. But these numbers and the time in which it is they bifurcates, they are not arbitrary. There's a beautiful correlation they are splitting up. So that's the beautiful observation which we obtained. So this is just a schematic, but I will show you what is actually being done. So this is one of the experiments, because this is the first one. I mentioned this, but there are many, that how this waveguide is created and BEC is actually observed. You can see there's a ring waveguide, and atoms are actually observing time of flight measurements in different time instants. Okay. So persistent flow is actually observed. So this is also kind of a paper in 2011 or 12. This is also the model of the experiment. So how it is created. So it is created by a simple harmonic trap, a 2D harmonic trap, and a Gaussian in the middle. You can see the Gaussian here, and then you have a 2D harmonic trap. So you actually have a minima position. Okay, so around this, so you have a minima. Now, if you think of the G Yeah, am I audible?
Yes, you're audible now.
Oh, okay. So it was disconnected somehow. I don't know. Okay, I have to share my screen. So I don't know how far I could tell. Yeah. So am I okay with the previous slide? I think this slide was the only one which I missed to in terms of network. So yeah, so this is the ring trap which is in experiment, but in theory it is very, very crucial, because you can form a double well by combining optical this harmonic trap with Gaussian, as it is kind of written here. But one has to be very careful about the slope, the frequency of the harmonic trap, omega, and the two parameters of the Gaussian trap, which is the width and the height, both. So three parameters has to be played very meticulously to form it exactly in the harmonic profile. And then you can have a very, very well-defined ring trap in which you can keep the BC. Okay, and this BC will be, because the ground state is Gaussian and coherent state is also of Gaussian shape, optical coherent state. So you can actually compare the state as compared to a coherent state, and this should be equivalent to a getting a situation which will have a nonlinear quantum evolution in this ring trap. Yeah, so is it? It's not moving. Okay. So now the question is, what happened to a long-term evolution? So let me show you this movie first, and then I'll tell you. You can see in the ring trap, in the experiment in 2016, that when the clouds are coming and merging, you can see a clear interference pattern. And then, it is very short time. Then beyond that, people have not much, analyzed. But let me see what will happen to a longer time. So, is a situation, I'm just stopping it somewhere. You can see that it is a very fast movie, because otherwise it will take a long time. And I'm stopping it somewhere. You see it is evolving. And if I stop it at arbitrary points, you can see several condensates are formed at different times. Okay, so I'm just stopping it at some particular arbitrary times, and you can see different numbers. But don't think that these numbers are arbitrary. Okay, and that's what we have analytically calculated the time scale, and also found the exact formula for the fractional variables, that how this is fractionally divided. So here is just for the students to tell you what is actually fractional variables mean. That if you have a coherent wave packet to start with at TFR equals to 0 times 0, red dots in the extreme left corner, and then at different times, which is indicated by the fraction definitely you can see the final time is 1. That's the revival time. So the cloud is coming back to the same place. And all these times are a fraction of that revival time. So the number of splits which is happening is depending on the denominator and the numerator of the time fraction. So that's the thing. So how it is related, that is the phenomenon of fractional variable. So here is the density snapshots. Okay, so you can see that at different time snapshots it can be taken of the condensate density, and which can take you to 2 splits and 4 slits and so on. So 6, and then there are this is 6, this is 5, and this is probably 12. Okay, and these are actually appearing in different times, which are according to our formula. So what is it? So the formula is here. The T is m by ntr, where the number of fringes, which is S, it depends on n by 2 if n is even, and it is n if n is odd. So denominator is odd, then it splits into, say, n equals to 3, so it will split into 3 condensate. If the denominator is 6, okay, and then also it will split into 3 parts. So this is the standard formula for fractional variables, which we analytically found this formula, and which you can see in the quantum carpet here. This is in X space, and this is in Y space, because it is a 2D system. And autocorrelation is a complicated one. You should look at only the red one, because that's for one soliton. But we have also checked that how it is time scales and other things that differs for 2 soliton. But the red one, you can see that here it is splitting into 1, but I have given the scaling 0.5 because it is actually reviving to the other side of the ring. So if you consider the revival to be exactly in the same position and same shape, then it is the half of the revival. But other places wherever these numbers are, the red numbers, these are the numbers in which the condensate are splitting. Okay, and this is exactly which is observed in the density snapshots. Now, if you look at the time scale, is a quantitative, numerical calculations, and compared with our theoretical results, you see that is an exact agreement of the theory and the numerical analysis. So numerical in the way that we solve the equation, we evolve the equation by numerical methods. So it's completely independent to the theory we have taken up. So, but then we see that this is the time scales are exactly matching each other. So this we have reported in recently here. Okay. So this is something which we can take it to a new direction. So this phenomenon was observed for the first time in BC. And we can take it to a direction of quantum information in this fashion. So it's a new direction. Now, this is one thing very interesting we found, that is a spatial interference in that. So the same system is a ring trap, but there is a 2 BEC, it's just for, symmetric arguments. You can also take 1 BEC, you have to wait a little longer, that's all. But what we do, we allow it to spreads, and then we switch off the trap, middle trap. So we switch off the Gaussian trap and allow the BEC to come to the center and overlap. Okay, so this is a spatial interference. You don't have to do, homodynamics and tomography and all. And so is a spatial interference when they're crossing the center. And but the beautiful thing is that when you have this interference pattern forming at the center, this is not what is expected. So we have taken the snaps of exactly at the center when it is concentrated at the center of the ring. Now it should be expected that the center it will be a maximum, then slowly there will be rings other than this ones, but this portion should have a kind of a Bessel function kind of structure, but it is not, because of we found a beautiful phase structure which is related to angular momentum. So this is something which is going on, but you can see a very beautiful spatial interference structure over there. Okay, now the last thing is the quantum sensing is a very important applications of quantum information. That is why how precisely you can measure the parameters. That's called the quantum sensing. Okay. Now here I use the system where BEC is experiencing tunneling and reflection. So when it is striking a wall, and then it has two possibilities. It can reflect back, and also it can tunnel through. And depending on the barrier, potential barrier, like how steeper it is and how much is the width, it depends on the ratio between the tunneling and reflection. So there have been a lot of experiments that to control the tunneling amplitude and reflection amplitude of the ultracold atom in presence of barrier. And so this is just one of them. The reflection was properly examined, and then tunneling was minimized, and there are many other methods where both were present, and then there are a lot of studies. Now I want to show you that this movie, density movie, in the middle one is the barrier. The red one is the barrier. Wherever you see the red spike is the barrier, and the blue one is BEC. Okay. Now you see what happens during propagations. It goes, it splits. Now I'm stopping it here. So I'm comparing this to a beam splitter. It comes and bifurcates and giving us a situation of Schrodinger-Katsted kind of situation. Now if you allow this more, and then you create more complicated situation, and then you see there are different situations where you can have a different kind of states which are useful for Planck structures, okay, and quantum sensing. So that's the idea for this. So this movie will go on for some more time, but then this is the same thing, inside the harmonic trap, they will keep on oscillating, but they'll create such kind of structure over there. So you can actually kind of compare with the atomic beam splitter inside a waveguide. Now this is one snapshot of that. at time 11.2 millisecond. So we have taken some experimental values of from the experiment of Straker et al. Solitary wave experiment, and at that time, this state will give you a subplan scale structure which is having kind of zeros all around this structure. So those kind of structure having zeros all around are very useful for quantum metrology. Okay, so it is in Schrodinger cat state, they are having zeros in one side but not the zero on the other side, because other side is decaying is a Gaussian, and Gaussian goes to 0 at infinity. So that is why these subplan scale structures forming of 4 states are more useful than Schrodinger cat state. Okay, so there's a beautiful paper which W.H. Zurek has started this scaling law, which is here. You can see A is h cut square by A. So it relates to the classical action. So the precision, that how precisely you can measure the parameter, it depends on what is the strength span of the quantum system. So which is also related to classical action. Now this is the thing which is precisely is you can calculate the classical action if you know the wave function. Okay, and then we have actually calculated these things by 2 ways, numerically as well as from the plots which we have got from our analysis. So we compared, and you see there's a beautiful agreement between that, and then this dotted thing is the fitting of these points T1 to T5 at different snapshots. So you can see the inset where the limit and classical action both, and we have seen that this scaling law is exactly followed. Okay, and so this is the first time that we are actually proving the scaling law for this system, because when it was started by Zurek, he mentioned about chaotic gas and also mentioned about the harmonic oscillator system modeled by harmonic oscillator. But this is not the system which is modeled by harmonic oscillator. This is a completely different system which is having a nonlinearity, and the propagation of wave is completely origin is completely different. So it was important to know that what is scaling law. But then when we use the scaling law now, so first we have established it, and then we found out this kind of sensitivity, and from the zeros of the Wigner functions and also numerically. So we found out very precise measurements of position and momentum. But then in addition to that, temperature sensing is something which we have connected from there, that we are able to propose that the measurements of few picokelvin temperature, which was not reported to any literature so far. In 2000 probably 18, in science paper, they have reported few nanokelvin. But picokelvin precision, to my knowledge, is not reported in the literature. But in this fashion, one can actually correlate. Is the indirect measurements of temperature by changing the so you can have a very
Hello? Anybody there?
Yes, sir.
I think Utpal, you are disconnected probably.
Yeah, there is some internet problem on his side.
Yeah, yeah.
He will join.
Okay.
Yeah, I'm sorry that, somehow network was disconnected. Am I audible now?
Yes.
Okay. So I was, towards the end only. So I was concluding that, ultra cold atom has been a very useful system for quantum simulation as well as quantum all kinds of applications for quantum information. So especially when you find a new phenomena in quantum information in this nonlinear system, that becomes always very interesting. And because it is a highly tunable system, as you have more possibilities to say, for example, if you want to create, say, 14 coherent states, and a situation of which we created in the ring trap, it may not be easily obtained in experiments, because to my knowledge, there are only 8 coherent states in a superposition in a ring is achieved in experiment recently. So this system being very tunable is a favorable candidate, and one can go up to quantum sensing up to a very good results. And these are some references for the students which is related to this. I have mentioned about mainly these two and this one, but starting from the paper from 2006 to this, these are related to this. Somewhere I have mentioned in this presentation. So this is the research group where these are PhD students and this is a master project student. I am thankful to the collaborators because they have helped me in different ways. So thank you so much. I can take some questions now.
Yeah, thank you, Utpal, for a very nice talk. Now let's look at the questions.
Yeah, there are a few questions in the chat box. Can you see them? You need to.
No, because I was network was out, so I cannot see all of them.
Okay,
Can
okay.
you please read for me?
Okay, then I can read it for you.
Please, yes.
So Deepan has asked, how does the coherence temperature limit in BEC depend on type of Hamiltonian and energy per degree freedom?
Can you repeat the question once again, because I find that
Sure. How does the coherence temperature limit in BEC depend on the type of Hamiltonian?
Okay, so you see, what I understand from your question is not very clear, because words are not very, but what I dig out from there, you are probably want to mean the critical temperature, which is depending on the external trap. So say, for example, you are doing it in an optical bench, and then you have a magnet optical trap over there. And so what should be the shape of the potential? And for that, how is it related to the critical temperature? Okay, so there is a if you look at the book by Pethiks, is a very beautiful derivation given there, which says that the parameter alpha, which I probably mentioned somewhere, I'll go back to the slide instead of telling the expression probably. So which is controlling the number of atoms in a major way. Yeah, so because I think this is precisely what is trying to tell me. This expression, if you see, there's a parameter alpha, which I did not mention because I thought that this is a fundamentals, one can go back to the textbook and find it out. But this alpha depends on the trap profile, trap shape. So if it is a kind of a box potential, it is of a different. If it is a three-dimensional harmonic oscillator, it will have a different value. So then it depends on the critical temperature also. Okay, so that's how it controls it. That's how. Okay, and in terms of the optical lattice, when you have a optical lattice, you can trap neutral atoms. So you can go to the internet and find SE stock sheet, how it is affecting that. So so is related to the perturbations, that how the second order perturbation, how it is affected, atom is affected. So yeah, so that's the thing.
There is another question. Is the optical lattice technique similar to optical tweezers? Are the underlying mechanism same in both techniques?
No, I don't find any connection in that. These are completely of different origin. Okay, so optical lattice is the standing wave which is created by counter-propagating lasers. Is very simple and easily doable in lab. So no, it's not. Yes.
Another one is, do the BEC characteristic like negative temperature also take place in photons in the optical lattice? If so, how does it influence the trapping?
Okay, so you see, I'll correct the question first and then I'll go with the possible answer from my side. You see, optical lattice itself is a superposition of photons, right? So it is a form of laser, so it can trap atoms. Okay, and so photon-photon interaction is not scientifically found out. So in that case, yeah. So what was the second part of the question? For negative temperature. Okay, so negative temperature, if you I don't know, photonic BEC is experimentally obtained, but the formation mechanism is completely different. So in circuit QED, people have been trying for this, and but negative absolute temperature, I don't know, maybe possible, but because the origin of BEC is completely different, I really doubt that whether it may be possible for that. But because it is a completely different scenario, creating an upper bound of energy will be from a different process in different physical systems. So the photon BEC is not formed the way atomic BEC is formed. Okay, so because the photons are not affected by electric and magnetic fields in this way, so it is not in that way controllable, so that you can form a BEC in some energy levels. So it is a completely different things, but there are discoveries of photon BECs in probably 2017 Nature and Science paper. So yeah, so one has to see that whether it is possible. It's not very easy thing to answer, yeah, from my side. Yeah.
So there is one more question by Deepan. Would there be any restrictions to BEC tunneling for system with upper bound of energy?
No restriction. You see, all that the atoms understand during tunneling is whether the barrier is enough for appropriate for tunneling or not. If I consider an optical lattice, if the lattice height is too much, then I can consider this system as a mod insulator. So it's not superfluid. So this kind of, what I'm doing is all superfluid kind of situations. I am not going to a situation where it is a kind of a solid situation or insulated situation. So the tunneling depends on the height of the barrier and width of the barrier. So whether you are doing it in a positive temperature or negative temperature, the atom being inside the trap will only understand that the neighboring sites, neighboring barriers are how much is the height and the width of the potentials. That's all. And you can see that in negative temperature in one of my slides. I'll just go back just once so that I can correlate. Yeah, so here you can see is a beautiful example of tunneling at negative temperature. So from center, if you see the 3D plot, it's tunnel to the left potential well and the right, and so on. And that depends on the height of the optical lattice. I should not make, and that's why the parameter, this beta, is controlling it. So if you make it beta too much, then it will be confined to probably the center only. It cannot go to a neighboring site. So that has to be experimentally handled if you want to actually observe tunneling and reflection. But that's why in the beginning of the example of tunneling and reflection, I mentioned that people have been trying for the experiment where one can tune the probability for reflection and the tunneling by changing the barrier.
So I don't see any more question in the chat box.
So if there are no more questions, let's thank Utpal.
Okay, sir. Thank you, sir. Thank you.
Yeah. So I have, I was not aware about some of these recent works with Salasnis, but very nice work.
Oh, okay.
It fits so well with experiment.
Yeah. So